Hey guys, welcome back. In this video I'm going to be showing you how to solve a fairly simple statics problem which involves finding the magnitudes of the reaction forces of the pins A, B, and C provided there is a 100 Newton meter torque acting on this assembly at point D. Alright, now in order to solve this problem, let's first talk about an approach to solving this problem and several problems similar to it. Well, first of all, we need to draw a free body diagram, and the free body diagram could be of the entire assembly, but you'll find that it's necessary, for the sake of creating more equations, that we need a free body diagram of our first part, which makes up our assembly, by which I mean this part just here. And we also need to do a free body diagram of our second part, which makes up our assembly just here. And I'll call this our second part just here. And in the process of doing that, out of necessity, we will also need to create an axis so that we can quantify what we mean by positive and negative when we're talking about directions. Okay, now once we've done that, we can actually analyze the free body diagrams using two main formulas, one of which is the sum of moments around any point is going to be equal to 0, and the other one is the sum of forces in the x direction is going to be equal to 0, and the sum of forces in your y direction is going to be equal to 0. And then once we're done with that, what we're going to do is we're going to solve the algebra. Right? We're going to be left with a whole bunch of simultaneous equations, and then we just need to solve them all in order to find our answer. Okay guys, that's going to be our approach. I strongly recommend you pause this video, have a shot at this yourself first, and then come back when you're done so you can compare your solution with the solution I'm about to get. Okay guys, so let's first start by creating a free body diagram of our first object just here, the rectangular looking one. Okay, well, remember, the pin B and pin C are in fact pin supports, which means that our reaction force is going to be split into both horizontal and vertical components, and I'll assume the horizontal component will be acting to the right, and I'll assume that the vertical component will be acting upwards, right? These are just assumptions I'm making out of the blue. And I should also mention that I'm going to be making the axis in such a way that x is going to be positively to the right and y is going to be positively upwards. I'm basically defining what I mean by positive and negative here, a really important thing to do. Okay, now because point C is also a pin support, that means that we're going to have reaction forces as well, which can be split into both horizontal and vertical components. The vertical component will be Cy, and the horizontal component will be Cx. And once again, I'm just assuming that Cx will be to the right and Cy will be upwards. We'll find out whether that's actually the case when we determine the sign of our answers. Okay, now that we're done with that, let's actually analyze the free body diagram of our second part of our object that makes up our assembly. Well, we know point A is a pin support, so that means we're going to have AX just here, and we're going to have AY just here, right? Not only that, but we also know we're going to have reaction forces at point C again too, but this is the tricky part. Remember, we've assumed that CX has directions which I've outlined in this free body diagram before, and because this is a separate object but still connected, due to Newton's third law, CY must be downwards on this and to the left on this one just here. I hope that makes sense. This is due to Newton's third law. Each action has an equal and opposite reaction. Also, we know free body diagrams show external forces and external torques, so that means we're going to have to also draw the 100 Newton meters in the clockwise direction here as well. Okay guys, now we're ready to get involved in the maths of all this. Before we get into this, let's actually define what we mean by positive and negative when we're talking about moments. So based off the right-hand rule, that means that counterclockwise is going to be considered positive. This is based off the right-hand rule. Okay, now in order to solve this, let's actually do the sum of moments around point B is going to be equal to 0. This is for our first object, I should say. Right, so let's do this. The sum of moments about point B, I could have chosen any point, by the way. I just chose point B out of simplicity, is going to be equal to 0. So let's do this. What is the moment due to our force Cx? Well, it's going to be Cx, it's going to be positive, because it's got a tendency to rotate this object around point B in the positive counterclockwise direction, meaning it's going to be Cx times by our perpendicular distance from our force towards our axis of rotation, which is going to be this distance just here. It's going to be this distance. We're going to be multiplying it by this distance just here, which we know, based off our question, is actually 0.3 meters. So we're going to be timesing by 0.3 meters, right? Now let's consider the force Cy. What type of torque does that produce? Well, it's going to be in the counterclockwise direction, so it's going to be positive, and it's going to be Cy, and it's going to be times by our perpendicular distance from our force towards our axis of rotation, which is this distance just here, which I've drawn, and that's going to be equal to 0.4 meters. That was given in the question. Are there any other torques? Nope, so that's just going to be equal to 0. Notice there are no other torques because Bx and By do not produce torques because the forces go straight through the axis of rotation. Okay, now let's get involved in the second free body diagram. And we could have done, I should mention that we could have done the sum of forces in the x and y here, but for simplicity's sake, I'm just going to focus on our second diagram and worry about the sum of forces later. So let's do the sum of moments around point A in our second diagram is going to be equal to 0. As a little bit of a hint for these types of problems, it's always good to choose sum of moments around the point which you do not want to consider the variables in your next equation. So I chose point A because I didn't want to have an equation in terms of ax and ay. That's so I can get an equation in terms of cx and cy so that I can solve for cx and cy. If that isn't completely clear, hopefully it'll be clearer later on in this video. So let's consider the torques done by Cx. It's going to be positive because it's got a tendency to rotate this thing in the counterclockwise direction. So we're going to be timesing it by our force Cx times by our perpendicular distance from our force towards our axis of rotation, which is this distance just here, which if I draw it on this big map is actually equal to this distance just here. It's this distance just here, and what's that? Well, we know this is 0.3, we know this is 0.4, that means this distance is actually 0.1 meters. So we're going to be timesing it by 0.1 meters just there. Now let's see, are there any other torques? Yep, there's going to be Cy, but it's going to be negative. It's going to be Cy, which is negative because it's got a tendency to rotate this thing in the clockwise direction. And it's going to be Cy times by its perpendicular distance, which is going to be this distance just here, which I'm drawing in this dotted line just there. That's going to be that distance, which we know, I know this isn't to scale, but it's actually going to be this same 0.4 meters, which I've got just here. It's going to be 0.4. Are we done? No, we're not. Notice this 100 Newton meter force, torque, I should say. It doesn't matter where it is. The point is that it's on our second free body diagram, so we need to include it in our moment balance, and it's in the clockwise direction, which is negative by our convention, so it's going to be minus 100, and that's going to be equal to 0. Okay, guys, that was by far the hardest part of this problem. If you can get that, then you are well on your way. Okay, so let's do this by first solving for Cy, and I'm going to solve for Cy from this equation first. We know that Cy is going to be equal to, let's see, it'll be minus Cx times by 0.3 on 0.4, okay? Then we're going to substitute that in here to solve for Cx. So that means we know Cx times 0.1 minus Cy, which we just figured out was minus Cx times by 0.3 on 0.4 times by 0.4 minus 100 is going to be equal to 0. And when you analyze that, you're left with the solution that Cx is going to be equal to 250 newtons. Cx is going to be equal to 250 newtons. That's after you solve the equation, which I've got just above. Okay, let me zoom out because I feel like this is becoming a little bit cluttered here. So let me zoom in a bit. There we go. Okay, now that we've got Cx, we can literally substitute that back into here. I know it's a little bit of a mess, but I hope you're still getting this. And if you solve that, you're going to be left with Cy is going to be equal to minus 187.5 newtons. Okay, so far so good. We've got our reaction forces in the x and y direction of our pin support at C. Now let's see if we can do A and B. Okay, fortunately for us, we still have a few equations under our belt. In fact, let's draw a free body diagram again so we can quickly understand that. This is our free body diagram of our object 1, remember? I'm just going to quickly redraw this. We've got bx just here, we've got by just here, and remember we defined cy up here and cx just here. From our force balance, we can say that the sum of forces in the x direction is going to be equal to 0. Therefore, we can say that bx, it's positive because it's to the right, plus cx, that's also positive because it's to the right, is going to be equal to 0. Meaning that bx is equal to minus cx, so that means that bx is actually going to be equal to minus 250 newtons. I hope that makes sense, guys. Okay, not only that, but we also know that the sum of forces in the y direction is going to be equal to 0, meaning that by, it's positive because it's upwards, plus cy, it's positive because it's upwards, is going to be equal to 0, meaning that by is going to be equal to minus cy, so by is going to be equal to positive 187.5 newtons. All right, that's our answer for by. Now we're going to do the exact we're going to do the exact same thing for our pin supports at A. Let's quickly redraw that free body diagram again. So we've got AX just here. We've got AY just here. Remember, because we've assumed C was in this direction in our first free body diagram, that CY must be down here and to the left here. And we've still got our moment just there. Okay, although our moment won't be too helpful for us because we're just going to do the sum of forces in the x direction is equal to 0. And what's that? Well, AX is positive because it's to the right, CX is negative because it's to the left, and that's going to be equal to 0. Moments don't come into this because it's not a force. Meaning then that AX is equal to CX, so we're left with AX is going to be equal to 250 newtons. Done, we've solved for AX. Now let's do the sum of forces in the y direction is going to be equal to 0, and AY is positive because it's upwards, CY is negative because it's downwards, and that's going to be equal to 0, meaning that AY is going to be equal to CY, which is minus 187.5 newtons. Okay, we are almost completely done. We've got our reaction forces in terms of x and y, but we were asked to find the magnitude of the total reaction force. So let's see if we can do that. In order to do that, let's just consider point B here. Remember, point B is this point just here. Notice that Bx and By are just our components of our reaction force in our x and y direction. So our total reaction force actually looks something like this. Our total reaction force actually looks something like this. Its components are just Bx and By. So if you were to redraw that in a triangle, it actually looks like this. This will be your magnitude of your reaction force at B, and this, in fact, it shouldn't have an arrow on it. This will be the magnitude of your reaction force at B. This will be your magnitude of By, and this will be your magnitude of Bx, just there, right? And this should be screaming alarm bells at you because this is a right-angled triangle, meaning then that we can use Pythagoras now to solve for our magnitude of B, right? And you can tell from Pythagoras that this is just going to be the magnitude of B is going to be equal to the square root of Bx squared plus By squared. Right? And this is huge because we can literally just substitute this in now to get our answer, meaning that the magnitude of our reaction force at our pin B is actually going to be equal to 312.5 newtons. That is your answer for your reaction force, your magnitude of your reaction force, I should say, at point B. Remember, reaction force is we're dealing with a magnitude here, so no direction necessary. Likewise, for the exact same reason, the magnitude of our reaction force at C is going to be equal to the square root of Cx squared plus Cy squared, which is going to be equal to 312.5 newtons as well. And let's do point A as well. The magnitude of our reaction force at point A is going to be equal to 312.5 newtons 2. Okay, cool. We are done now. Remember, we're dealing with magnitudes, no direction necessary. That is our answer. This, and this is our answer. I hope that makes sense, guys. Just as a brief reminder, we're dealing with cx squared, cy squared, bx squared, by squared. Oops, I should have written a squared there. And ax squared and ay squared. And because it's squared, it doesn't matter what the coefficient was here, whether positive 1 or negative 1, it's all going to come out the same. Okay, guys, I hope that makes sense. And I'll do a few more videos to really hammer down this concept.